On this figure you see illustrated elasticity problem. This is some domain where we have some force here. This domain is connected to this region, and there is a vertical force in this point pointing down, and this makes this object be deformed downwards. And in order to find all these deflections and all forces, stresses in the structure, we have to solve an elasticity problem, which may be of such a form, such general form, which we have seen many times before. In this case, this space capital V is in fact a vector valued function space, and more complicated than the heat conduction problem, which we have seen many times before. It's completely impossible to find the exact solution U to this problem. So what we can hope for is to find numerical solution of it, and the numerical solution, which is illustrated here, is done by using the famous finite element program ANSYS. Students are able to use it at Narvik University College, for example. Well, we are now going to say some general words about the finite element method. The finite element method is in principle very simple. The principle is as follows. We, instead of using the whole Hilbert space, capital V, you take a finite dimensional subspace of this space V, and this space has m basis vectors, and we call this VH. H is associated with the smallest length in our triangulation. We will come back to this later on. Any function in this space is of the form xi1 v1 plus xi2 v2 and so on up to xi m vm, where we have assumed that we have m basis vectors. So what we are doing is to replace the original Hilbert space with just this finite element space. One simple example is the Dirichlet problem, and we will only consider the Dirichlet problem in this course for simplicity. We know that this Dirichlet problem takes this form. This is a standard Poisson equation, or not so standard because we have this lambda maybe a function of x, so it's a little bit general than the most simple Poisson equation. And on the boundary we assume that u is 0. We have that the weak formulation of this problem takes this form. We have seen this many times before. Let us now assume that omega is some has a boundary which is a polygonal boundary, like I've tried to illustrate on this figure, and that this region may be, in this case, a convex domain, but this is not important for the method. It's just simplify it a little bit, but it's not important. What we are doing then is to make some discretization, triangulation of the problem. We can, for example, use these does not need to be triangles, but we will assume that we will, for simplicity, assume that there are triangles. Um, However, in the general case, we can use any kind of polygonal triangulations. We will now define what we mean by this h. This is the maximum diameter of K, where K is taken over all triangulations TH. And the triangulation TH, what is that? It is the set of all such triangles. So we let the interior of any such triangle be denoted K1, K2, K3, K4, and so on, up to Km. So we have a finite number of triangles. And associated with each of these triangles, we have node points. We call this the first node, this the second node, the third node, and so on. And we call n1 the coordinate of the node 1, and 2 the coordinate of node 2, and so on. How to count this is maybe different for different cases. Note now that omega, the whole domain here, is just the union of all these triangles. What we will do is to let us just go back here and define more precisely what we mean by this h. The diameter of a triangle is defined as the longest side of the triangle. So, for example, for this triangle, the longest side may be this side, and we call the diameter of K the length of this side. So when we find the maximum length in all of omega, then we call this maximum length h. So, well, where do we see this maximum length? Maybe this side is a maximum, the longest side in this triangulation. So then h would be this length. Okay, what we do with this finite, in order to define a finite element, a finite dimensional function space of this Hilbert space, we do as follows. We consider functions omega, where omega is 0 on the boundary, continuous, and a first order polynomial on each triangle Ki. So if the triangulation is like this, that we have only triangles, not other kinds of polygonals, then it's natural, or we will at least assume that the functions are linear on each of these triangles, just for simplicity. But they could be second order polynomials, third order, and so on. So, of course, this finite dimensional space is now a function space, which is a subset, finite dimensional subset of W0. We note that w of ni is just the function value in the node point with node I.